Well, we will go on. And if you have questions, we can still address them at the end of the presentation. So before talking about digital human control, we have to talk about digital human models. For now, we only talked about motion capture data, which are only position and rotation in space. But digital human models, they are 3D representation of humans in a virtual space. And these digital human models, at the end, they will be controlled to follow the motion capture data. Usually, these digital human models, they consist in three different models. First, a skeleton. In 3D animation, it's also often called a rig, a skeleton rig. So this skeleton is made of bones and joints. The second point is that you also need a set of muscles. So you need to model the muscles put on the skeleton. And at the end, the third step is that you would need a skin on this digital human model. So there are different kinds of digital human model. Some of them only consist of a skeleton, and some of them they will add a set of muscles and a skin on top of it. But the basic digital human model, they only use a skeleton, for example, and sometimes they put a skin on it. It really depends on the applications. First, we'll focus on the definition of the digital human model skeleton, or the rig. So as I said, it's a set of bones, and these bones, they are linked together by a set of joints. I can give you some example. Here in the two pictures, you see here a hierarchy of bone. I guess it's one from the perception neuron software. So you have two legs, you have two arms, you have neck, head, you have different bones to define the lumbar spine and the thoracic spine, and you also have different bones to model the fingers and the hands. On the right side, you have a different skeleton definition. It's the one used by the Stereolabs body tracking. As you can see, it's quite different. The feet are defined with different body IDs. So you have the foot tip. You also have the knee. And the head is also different. You can have some IDs for the eyes. You can have some IDs for the ears. And also the hands are different, meaning that you can have the hand tip and the thumb tip, but it's not so precise regarding fingers. So the idea is that you have a hierarchy of bones, and what is important to see that the anthropometry of this digital human model is actually defined by different length and mass. So each bone has a different length and mass. And also each joint have specific degrees of freedom. So this is called the kinematics of this tree. As we see that each digital human model can have a different number of bones, it can have a different hierarchy, and it can also have different degrees of freedom. About digital human model anthropometry, so it's defined by a set of lengths and mass. Usually, the most basic way of defining the anthropometry is by giving precise dimensions of the human body you want to model. So you would give the total height, you would give the height of the head, the height, the length of each line, and you also give the mass of each line. This requires you to measure precisely each length of a specific user. It's quite time consuming, and it doesn't really apply to different users. So you have to do it for different each specific user. Usually what we do in simulation for defining a digital human model is that we use templates and databases in order to generate an average digital human based on different high-level parameters. And these high-level parameters, they can be the total height of the human body. It can be also the total mass of the human body. Or it can also be the body mass index. The body mass index describes if you're underweight or overweight. And another high-level parameter is the percentile. You would give a percentage like 5%, 50%, 95%. And this percentage defines in which part of the population the human body is put. So 5% means that you are under the 5% of the total human population. So it will give you a small height and a small mass. These are the data you usually give. And here are some examples of the databases that are commonly used. You have Answer1, Answer2, Nance. These databases, they come from American survey in the US Army. So they give you average data of plenty of people that have been measured. And this data can give you average length of bones, average mass of bones also. Based on this database, you can also use some proportionality constants laws. And here I have a link, which is a toolbox in which you can actually give a height, and it will give you some average bone length. So this describes the anthropometry of the digital human model you want to simulate. When you have defined your anthropometry, then you need to define the digital human model kinematics. And the kinematics is described by a set of joint parameters. These joint parameters, they can be the degrees of freedom for each joint. So these degrees of freedom describe in which axis the bone is rotating. You can also define the joint limits, meaning that your elbow cannot move more than below 0 degrees, and it cannot really move above 180 degrees. You can also add some joint damping and friction, and these joint parameters, they can also be controlled, and so you can add some joint forces to control this mannequin. Here you have two examples of digital human model kinematics. So for the one in the middle, you see the whole hierarchy of bones, and for each bone you see each degree of freedom. So the waist is a free-floating base, so you have 6 degrees of freedom in space, so the position and the rotation. Then the first segment is the lumbar spine. It can move in it can rotate in 3 directions, X, Y, Z. Thoracic spine can also rotate in 3 directions. The head here can also only move in 2 directions. And it's the same for the shoulder, the arm, the forearm, hand. Basically, you can have between 1 to 3 degrees of freedom depending on the articulation. And on the right side, you can see the description of these kinematics also. when you have defined the digital human model skeleton, then in some cases you want to also to model the muscles. And it's especially needed if you want to do precise ergonomics evaluation, and you want to compute internal efforts and internal muscle efforts. Then you need to have a digital human model with muscles. These muscles model are quite complex to define, because you have to define where to locate the muscles on the bones, how to fix them on the bones. You also need to know how to activate these muscles, so by providing a force or an activation level on each muscle. And it also gives a really high number of degrees of freedom in the model, because if you only have a skeleton, then generally you would get something like 50 degrees of freedom. Each degrees of freedom are the ones of the joints here. But when you add muscles, then the number of degrees of freedom is really increasing, and it's also gives you more complexity um, to how to control these muscles in order to give specific position of the bones. So it's quite complex, and you have dedicated software to help you model these muscles on your digital human model. The most well-known are the OpenSim software. OpenSim is open and free software. You also have the Anybody software, which is not free, and you have to buy a license to use it, but it's the most precise and used for muscle digital human models. Another example is the custom toolbox, which is a French toolbox from research activities at CEA. And here is a short example of a cycling activity that is performed using a digital human model with muscles. And so they study the contact points on the bike, and they study how to activate the muscles in order to compute this motion. And they also analyze how the muscle activity is performed and if it can lead to ergonomics bad situations. So we talked about digital human model skeletons, digital human model muscles, and the third step is about digital human models external skin. So you have your skeleton, you have your muscles, and at the end you put a skin on top of your digital human model. Usually these skins, they are generated by templates and high-level parameters. These high-level parameters will give you freedom on actually how on the weight of the person, and they will give you some way to parameterize your skin at different body sections. So they will give you some more overweight part on the hips, some more overweight part on the neck, some more overweight part on the thighs, for example. And you can, so you have a complete set of parameters to actually generate your skin. Some examples are the SMPL library, and now you can also use the Ready Player Me avatar customization or the MetaHuman. They can provide also a toolbox to generate your skin. At the picture at the bottom of the slide, you can see different skin generation. So you can get different heights, and for each height, you would get different external skin, depending on the total mass of the body and depending on the actual morphology of the user you want to model. About external skin, it is actually quite important to understand and to distinguish between different types of skin. So the one I talked about is mostly the external skin representing the user's morphology. The second type of skin would be more for 3D animation, and it would be the graphics skin used for avatar display. And it's mostly the one that you would generate thanks to Ready Player Me tools or MetaHuman tools. That's what you see on the images on the right side. So they are able to generate a certain corpulence and a certain morphology, but they will also add some clothes on the skin. They would add different avatar display for the hair, for the eyes, for the nose, etc. And this kind of skin is mostly used for 3D animation at the end of the pipeline. And a third type of skin you have to distinguish is not really a skin, but it's a set of primitives, such as capsules or spheres. And this set of primitives is actually used as a collision mesh, and it's used for performance issue. We will see it later on in the presentation, but when you use physics simulation to control your digital human model, then you need to compute precise collision with the environment, especially with the floor, and you cannot really use the skin at the top of the slide here for this animation and for this physics control. So what people use is a simplified mesh that is a set of primitives, and it's really a convenient set of capsules and primitives used for physics simulation and to increase performance and time. Okay. A last word about digital human models. Here we saw about how to model the anthropometry, the muscles, the skins. Basically, you would give manual inputs, such as precise bone lengths, or you would give high-level parameters, such as the total height and total mass of the user. Nowadays, you also can extract automatically these kind of parameters with specific technology and scanning technology. You can have low-cost depth cameras, such as the Kinect Azure, or also the Stereolab Z camera. You just have to put the user in front of this camera. This camera will give you the skeleton of the user. Based on this skeleton, you can get the exact anthropometry of the user. And since it's a depth camera, it will also give you some details about the external skin, as you can see on the picture. And based on this information, then you can imagine to compute automatically your digital human model based on the scan performed by the camera. This is low-cost technology, and you can, if you need a really precise study for a specific user, then you can also use expensive camera setups, as you see on the picture on the right side. This kind of setup can use a set of hundreds of cameras. It can be 2D cameras, it can be 3D cameras. It can use 20 to 100 cameras. They are located around the user, and they are synchronized in order to instantly scan the user. It will give you the same process as for depth scanner, but it will give you some more detailed model of the user that is scanned. And it will also give you a more detailed external skin with textures and can give you a really photorealistic avatar at the end. This kind of technology is only used if you want a specific digital human model for a specific user. If not, you would probably prefer to use templates and total height and total mass as inputs. To come back to motion capture software, we saw plenty of different motion capture software used to control, to connect, and to stream different motion capture hardware. What is important to understand is that most of the time, each motion capture software will define their own digital human model. I gave you some examples here. The left side of the slide is for the XR Ergo software. So you have a specific bone hierarchy, and you have specific also bone colliders. You have specific joint degrees of freedom. The picture on the middle is quite an old picture from the ART human software. As you can see, you have also specific bone hierarchy with different degrees of freedom for the lumbar spine. The picture here is from the Xsense movement documentation. You get different hierarchies and different degrees of freedom for the lumbar spine, for the neck and the head. And the picture on the right side is from the Delmia and 3D Experience software suite. And they define also their own digital human model with different degrees of freedom, different hierarchies, and also specific different skins that you can put at the end of the avatar. So again, unfortunately, there is no real standard about how to model your digital human model. And each motion capture software will give you their own representation. So at the end, you have to adapt and to choose which digital human model you want to use, which hierarchy, how many degrees of freedom you want to use, especially to model the lumbar spine, for example. Do you want a precise model, or do you want a less precise model? What kind of morphology you want to use, etc. This ends the section on digital human model. And this section was preliminary needed in order to talk about digital human control. Maybe if there are some questions about digital human models, feel free to ask them. And if not, I will go on with the digital human control. Okay. So digital human control, it actually consists in animating a digital human model in order to follow or reach trajectory targets in space. These trajectory targets, they can be provided by animation, or they can also be provided by real-time motion capture. And these trajectory targets, they can be of different types. They can consist of only rotations, and it can also consist of Cartesian data, which means position and rotation in space. Here you have some example of 3D position in space, digital human model in a static pose. And at the end, what we want is to have this digital human model be moved so that it can correspond exactly to the motion capture targets. On the right, on the bottom of the slide, we see also different pictures. The red cubes that you see, they are motion capture targets. These motion capture targets can move in space, and at the end, we want the digital human model to follow these targets. Maybe I can show you a short demonstration about how this can behave. So I will just exit the presentation and show you a short software. So this will be a live fine. So I'm launching the software. So this is a software developed at CEA, which is called XR Twin. It's also industrialized by LS Group. So I will first define a mannequin. So maybe the screen sharing can give you some lagged vision, but I hope you will understand the main part. What I can show you first is that we can generate mannequin here. We can give some different input for height and mass. So here I can define a mannequin whose height is 1.9 meters and 100 kilos. If I decide to have, then I can say that now it's 60 kilograms. I update my mannequin, and I will go back to 1.7 meters. Okay, let's do a simulation with this kind of mannequin. I will go to my simulation window, and here what I want to show you is that I can actually move some of this red sphere in space. So here I'm using only my mouse to move them, but you have to understand that it represents some positions. The red cubes, they represent position that the virtual mannequin has to follow. So here I move them in rotation like that. Rotation, okay. I can give a specific posture for the head, for example. Okay, let's do it like that. Fine. I could also decide to move the legs, okay, like this one. This is the waist, okay. And this is what we, when we talk about digital human control, this is what I mean, okay? So we want to define some desired position, and the human mannequin has to follow them. What is interesting to understand is that I can give some targets that are out of reach, either in position or in rotation, but I want the virtual mannequin still to follow. Okay. I will end the demo here and go back to the presentation. So the easiest way to control the DHM, the digital human model. Okay, here is basically to control each bond. Oh, maybe there is a question. Maybe okay, yeah. Feel free to ask
Yes,
it.
I just like to ask a question that you, in the previous case, on the joints, you are choosing the square, like
Yeah.
like a block. However, normally the real human arm is basically having a different degree of freedom, not only, for example, the prismatic joint.
Yeah.
So are you also modeling inside this joint also like revolute joints or not?
So the human body I showed is only revolute joints, okay? But we could define prismatic joints if needed, even if it's not biomechanically plausible, okay? The human body doesn't have any prismatic joints. So here the model I showed is only revolute joints, okay? And then maybe I didn't got your question correctly. So
No, I think it's clear, because I think with the block I was thinking that it is only the prismatic joint, or like the model between two links was basically the prismatic joint, but as you have mentioned, it is basically more on the in the revolute joint. So I think it's more now clear with your explanation. But one more question is, can you change the damping properties of the revolute joint, or is just like normal connect link between two links?
so so you are talking about the joint parameters here of the human body we use, right? The joint damping and
Correct. Yes.
or the joint damping of the control.
No, no, joint damping, for example, when you say about the control of the human joint, two links are being connected. So these joints normally, what are the parameters you normally are updating? Is just a position, or also some damping or stiffness parameters?
So we have a specific damping and stiffness for internal joints of the human mannequin we show here, okay? This can be changed, but here we use some template parameters that comes together with our digital human model, okay? So it's a template. Uh, it has specific damping parameters. You cannot really change them, but it could be possible if needed. So this concerns the digital human model. And then on the control part, then as I will show in the next slide, indeed, you have some damping and stiffness parameters in order to make the human model follow the targets. These damping and stiffness parameters, they are actually input inside the software, and they depend on the mass of the human body, and they also depend on the mass of other objects the human body has to carry. So they have some default parameters here that are given in order for having the best control possible. And then you could modify them if needed. So I hope it answers your question.
Yeah, thank you very much. Yes, I do. Thank you.
Okay. All right. Anyway, it will get even more. You would get more answers in the next slides. Anyway. Uh, so the idea is to control the digital human model so that it can follow some targets in space. Uh, so the easiest way to do that is to apply some specific joint angles to the human body. Well, this is called forward kinematics. I'm sure that plenty of you are already familiar with this process. So that's what you see on the left picture here. You get you give an angle for the shoulder, you give an angle for the elbow, and at the end it gives you a specific posture. The thing is that if you want to reach a specific target in space, then you need to compute automatically what should be the jet angles to reach this target. And this is called inverse kinematics. And these pictures show you an example of inverse kinematics, either for an arm reaching a target in space, or at the bottom, you see two targets representing the feet position. And at the end, inverse kinematics algorithm would be used to actually move the legs so that it can follow this target in space. So there are plenty of forward kinematics and inverse kinematics algorithms. They are really easy and uh, easy to use and to implement, and they are commonly used for animations and video games. The main drawbacks of these algorithms, especially inverse kinematics, is that it does not always consider the body constraints, so the joint limits. It doesn't consider if a target is switchable or not. It does not also consider some physics parameters, such as the mass of the bones. It does not always consider the collisions with the environment also. So, and mainly all these drawbacks can actually be gathered and said that this inverse kinematics algorithm does not provide physically processable values. So it's mainly used for animations, but it will not give you some physics consistent values. Instead of using animation algorithms, for digital human control, the idea is to use physics engines in order to develop control laws and control algorithms to control the digital human model in a more physically plausible way. These physics engines, they will apply forces on bones, they will apply torques on joints, they can also, depending on the physics engine, they can also apply forces on muscles in order to control the digital human model and in order to reach specific configurations. I like this schema here, for which you see really the distinction between joint torques that will move the bones relatively to each other, and muscle forces. These are two different motor controls possible to move the bones. Either you move the joint, either you apply forces on the muscles. Here I give some example of physics engine commonly used in video games. So you have the NVIDIA physics engine, you have the Dart physics engine, and you also have the XD physics, which is the physics engine we develop here in my lab at CEA. And all the examples and videos and demonstrations I show you are made using this XD physics engine. If we go on with the physics engine, so they enable to develop more complex control algorithms. As inputs, you would get the motion data and the force data. And as outputs, these control algorithms will give you the joint quantities and the muscle quantities that you have to apply to your digital human model in order to follow the motion data and the force data. The most direct way to develop these control laws is by using proportional derivative controllers, so PD controllers. PD controllers, what they get as input is a desired position, a desired velocity. This position and velocity, they come from the motion capture sensors or from the animation data. These controllers, they can be seen as spring damper systems. So they have to be parametered with stiffness and damping gains. So maybe that was your question earlier, Jawad. So we have to parameter stiffness and damping gains. And these gains, they have to be parametered in an optimal way so that the control is optimal and that you can reach the targets in the less time possible and without oscillations, okay? And so here you have some pictures explaining you the process. So you have inputs at the beginning, you have a complete skeleton, and you want to control your digital human model to follow this position. And you can actually see it as if there were plenty of springs tearing your digital human model in order to be superposed to this 3D and 6D data. That's really the idea. These springs, you can parameter them in the Cartesian space, meaning that you have really position in space and you want to move them in the Cartesian space. You can also have these PD controllers in the articular space, meaning that the input is only angles, so giant angles, and then you would give as desired position these angles and move your joints, sorry, uh, to reach these joint angles. So this is the most common way of doing it, and it's quite easy. Then I will go into more complex algorithms now. So there are some equations. I will not go into details if it's not clear for everyone. So I'm sorry for now. It's not really for beginners here. It's a more complex slide and more complex explanations, but it's good to know. It's an example of quadratic programming problem that is actually used in the humanoid robotics field. Usually in the humanoid robotics field, the control of the humanoid robot is written as this kind of problem. So it's a quadratic programming problem, a QP problem, in which you have to minimize some objectives by keeping some constraints. The objectives of the problem, first, they can be that the humanoid robot has to follow and reach some targets in space. It has to maintain its posture, so its balance, and it also have to minimize torques. We don't want to explode the motor of the humanoid robot, so we want to keep it low. Uh, these kind of objectives, they can you can give them some different weights, meaning that your priority would be to maintain the balance of the robot, and then secondary, you want to reach some targets. Uh, and then when you want to minimize these objectives, you want also to keep some constraints. These constraints are relative to the joint limits. So you cannot give joint values that exceed the limits of the robotic system. You also have some torque limits, meaning that the motor of the humanoid robot have some limits. You also have some non-sliding contacts on the ground or on other surfaces. And also, a really important constraint are the equations of motion. That's what you see here as the last equation. These are the equations of motion of the robotic system, and it's seen as a constraint of the QP problem. I will not really get and give more details on this because it's not the aim of this presentation. If you have specific questions or comments on this, please, we could handle them at the end of the presentation. But what is important to know is that by solving this problem at the end, we will get the torques to apply to the joints of the humanoid model so that it can follow the targets, maintain balance, and maintain posture. Oh yeah, sorry, there's a sound here. Here I can give a short example of one of my PhD students, dates back last year, 2022, in which we can control a digital human model with specific Cartesian position, and also you can give some specific force to apply on the environment. And so here you have different examples on reaching a target on the ground, maintaining balance while staying on only one foot, reaching targets on the environment here, and applying some forces. All this is done by solving this QP problem. So This is all for the physics engine, but I really wanted to focus on why it is important to use physics engines rather than traditional animation tools, and especially when we talk about ergonomics evaluation. First, it provides a better physics consistency of your digital human model. It's not only animation, it will animate your digital human model, but by keeping your biomechanical constraints and also your joint limits, etc. So it will give you really a better physics consistency. Then you can also, if you are in a specific environment, in virtual reality, for example, you can also keep collisions with the environment. The physics engine can provide you with that. Using a physics engine is also a really easy tool to use if you want to do motion retargeting, because the physics engine will solve it quite easily. If you want to map your motion capture targets into different morphologies, then it's quite easy to do with a physics engine. The physics engine also, in the end, and that's really the main point of this presentation, the physics engine will provide you with efforts computation and also some more advanced ergonomic studies that you cannot perform if you use traditional animation algorithms, okay? There is also one last point. This is new trends now in virtual human animation. I give you some examples here about the Unicorn library, the Marathon Elms library also. You also have the Super Strike from Ubisoft, and you have plenty of them now in the next few years. The main point here is that nowadays you have plenty of new artificial intelligence tools and libraries that can provide you a toolkit or an environment in which you can train your physics-based characters. Because what you see when you solve this kind of problem, QP problem, you have plenty of parameters to know and plenty of parameters also to give. In the other PD controllers here, you have to give stiffness, you have to give damping gains also. These parameters, they are quite hard to know in advance, and this kind of environment can be used in order to train and to better know these parameters. And by doing plenty of parallel simulations, and at the end, it will give you the optimal parameters in order to control your physics-based characters, okay? So it can use some deep reinforcement learning, it can use imitation learning. As input, you can have a database of animations, and the idea is that this toolkit will spend plenty of time so that at the end you have the correct animation of your physics-based character. This is ongoing work. This is not from our lab, it's from other toolkit, but it's definitely something that has to be known and has to be followed in the next years, because I guess it should be the future of physics-based character animation, actually.